Today what we'll be talking about is a subject that's a little bit different than what you'll see in typical statics. We're not solving a problem in terms of finding forces. What we're going to be doing is looking at a physical property that's really based simply on geometry. And you'll be using this when you get into mechanics and materials, because we're going to be using this in terms of how we describe beam bending. But in terms of the book, it's called moments of inertia. Other terms you might hear it described as, and probably a little more accurately in terms of the way we're going to use it, is second moment of area. Now remember, we had a first moment of area, that Q that we were playing around with. It's related to that. And specifically, what it's used for is we're going to be talking about how this internal force is distributed across the brain. Because right now, remember, when we cut a beam open and we look at it internally, what's going on, we get a couple of straight forces, a vertical force there, our shear force, an axial force, and then this curlicue thing. Well, basically, that doesn't necessarily describe everything. When we get into mechanics and materials, we're going to be looking at what we call stress, basically a distribution of that force across the section there. So it's used for that. The other, where it really gets its name, but it's related, where it got its name and where it was developed was basically looking at accelerations. When you get into dynamics and stuff, you'll be able to understand what it means there. But basically, what sort of torque is required to develop a certain acceleration. But what we're going to be using it for really is this first part here, and hence the name second moment of area actually makes a little more sense. So what I'm going to do is kind of walk us through the steps to get there. Our first thought going back to everybody's favorite project, fluid pressure. And remember when we talked about fluid pressure, it varies with the depth. And how does it vary? Linearly. So again, we'll think about a gate. We've got a body of water there. We'll call this point O. And the distribution of pressure looks like that. It starts at 0 at the water surface there, and then develops some level there at the bottom there based upon the pressure. And we measure h, but I'm going to call it y this time. It'll make a little more sense when we start going through the calculations. But again, to calculate that equivalent force, basically, remember, it was just simply that triangle, but also remember we had that width to worry about, b. So it's that triangle, so we start off with a 1/2 times the pressure at L times the width, b, and then times the L. So this is our pressure. And this is our area. Remember, pressure is going to be force divided by area. We multiply times an area. We'll come up with an equivalent force. Oops, I think I'm missing my L there. Again, in the English system, the pressure was described by that specific gravity and then how far down we are. If we were doing it in the SI system, then it would be density times the acceleration of gravity, rho times g. But again, that depth, and we didn't put the depth there, we'll call L. And we calculate then that equivalent force. We know where it acts because it's going to be acting through the centroid of that area there. And then we can go ahead and calculate a moment about O or a force on the pin, that sort of thing. Now, because you guys love math so much, we're going to consider doing the same problem, but we're going to integrate it. Instead of using this composite area there, we're going to take this area and hopefully come up with the same result. Let's see. And what we're going to do is we're going to basically take a vertical or a horizontal strip basically of dy, go down from dy and calculate this same equivalent force. So basically all we're going to do is just integrate that. We're going to calculate that area under that curve there. Now noting that our dA has got some width to it here, so we've got our b width there. And then it's going to be dy thick. So to write that same expression, that's not rho, that's a p, sorry. Is again, we're going to integrate that pressure times the area there. Well, the pressure now is gamma y, because depending on where my integrand is, my y basically is going to be moving down there. And then noting my area is going to be simply b dy. Okay, so you're going, what the heck? We went through this calculation. Why do I care?
The integral is that rho dA?
No, that's a p. Sorry, that's supposed to be pressure. So it's pressure times that area. So what we're doing is taking that little bit of pressure that's acting on that infinitesimal area there, doing an integration across that whole triangular area there, and coming up with the same result that I knew all along. Where we're going to go with that, though, is what we're going to do is now consider that calculating the resultant for that equivalent force. What I'm going to do now is I want to calculate the moment about O using this same process by integration. So I'm going to use the same integration approach, but the trick that I have to do in terms of calculating the force was just simply the area under it. When I calculate moment now, I've got to consider the moment arm. So when I set up this integration, I'm going to set it up like this. So this part's the same, which is the calculation of my force, but now I've got this extra moment arm floating along there, and the moment arm is going to be based upon how far away I am from O. So again, I'm going to be looking at an infinitesimal area, infinitesimal pressure against an infinitesimal area there, or pressure against an infinitesimal area there, and then I've got this moment arm y, and I'll vary that along the way there. If I keep going with that, I'll leave it like that. I'm not going to worry about the B knowing the dA, so I'm going to keep it general. I'll keep it general with the dA there. But what we find then is we have this term that appears quite a bit in terms of when we get into mechanics and materials. And this term appears rather regularly. Sorry. And what we're saying then, this is going to be defined as a moment of inertia or second moment of area about the x-axis. And again, think about your perpendiculars. It's about the x-axis. Our moment arm is going to be then perpendicular to that. The other thing, too, so where we've been using x and y in terms of beams, we were using the y as the vertical, and then the x's are along the beam there. Now we're going to look at a cross-section of beam. We're going to cut it and basically set up yet another coordinate system with x and y there. So when I talk about the I of x, then note that my moment arm will be that perpendicular distance there, or that y. So just a little change there in terms of our coordinate system, but unfortunately that's the way all the books are, so, and that's the way all the tables are when we get into steel and concrete. Okay, so why do we care? So let's recall what we were talking about. When we cut a beam, we had a section like so, and then we had vertical, we had our shear force, we had our axial force, but the one that was kind of this bugaboo was this M. What we're going to find, especially when you get into mechanics and materials, what's really going on there is a distribution of forces like that. And when you think about it, these are two triangular areas there. We'll have a force there and an equivalent force there. So what we have is not this twisty thing really, but actually two equal, opposite, but non-collinear forces that are creating this twist. But in real life, it's going to be this distribution So what we're going to see, this actual distribution of these forces, it looks like a distributed load on a beam like we've done before. But again, stress is going to be across an area now instead of across a length. So hence the term stress. The word stress then basically is going to be describing this internal force that's going on, but it's going to be describing it across the area of that cross section that we've cut out there in terms of x and y in that direction there. So what we're going to find then is then in beams and in the range of the beams that we're designing and that sort of thing. So we're not talking about rubber beams and that sort of thing, but when you think about concrete, when you think about steel, visibly you're going to see maybe a little bit of bend. But what happens is what we're going to find is that the distribution for the most part and for the most of the areas that we're designing for are going to be this linear distribution. And that linear distribution can help. The way we're going to be able to describe that is with this magical little term called the moment of inertia. So if we think about this distribution, what we're going to describe it now in terms of, to be able to calculate that moment, is going to be describing it now instead of fluid pressure. It's going to be in terms of this stress distribution. And again, it still needs a moment arm. And the distribution is force per area. So we're going to have to multiply it times an area to come up with an equivalent force. So again, we end up with this magical little term, the y squared dA, which is basically going to help us which is basically going to be a physical measure then that we can measure on any piece of material, but it'll give us an idea then of how this distribution occurs, how much stress is going to be needed and basically to resist some sort of a moment or to create some sort of a moment. One note. It only depends upon the geometry of the section. So when you get into mechanics of materials, when you start thinking about things, you'll see why we have things like I sections in beams, why we have box sections. In concrete, generally it's usually square, but there's T sections and that sort of thing. So all of these sections are going to exhibit some different property here that's going to basically manifest itself into some sort of a stress distribution that's to our benefit. We basically want to design it so our things don't fall down. And because it depends upon the geometry, then what you're going to find is then you'll be able to open up books and find books like if you open your steel manual, there's going to be moments of inertia for all sorts of different shape sections there. Concrete the same way, composites also the same sort of thing. So basically what they've done is a lot of the work for you. A lot of that stuff will be out of the way. I've got one eraser. Okay, so what we're going to be then looking at is material sections. I'll draw a boring And again, just keeping in terms of our Cartesian system there, keep in mind that moments are always going to be those perpendiculars there. So if I'm measuring an I about the x-axis, I'm going to have a y moment arm. Vice versa, if I'm doing an I of y calculation, then I'm going to be looking for x as my moment arm. And then there's a third one. And why your author uses J, I don't know. But we do have circular sections, and we don't necessarily want to deal with the square system there. So there is another alternative, the polar. And instead of an IR, he uses J of J naught. So why, I don't know. But
being rotated like in a circle or rotated around a perpendicular axis to that?
it's rotating about a perpendicular axis on that, yeah. So if it was, think of it, if it was a circle, then again, you're going to want to be bending about some sort of an axis like that. But the nice thing about a circle is that you can do it anywhere. Ovals, you get a little more complicated and that sort of thing. But it's a little easier in terms of when you're doing circular sections to be using the J naught. Now the nice thing, though, is and a good relationship to keep in your head there is that J naught is going to be equal to the sum of the two. And the reason why is that we're describing a circle there, basically. The r squared is going to be equal to x squared and y squared. It's Pythagorean. And just to check yourself when you're doing all these wonderful calculations and that sort of thing, you want to go along there and check. If your answer is not in terms of length to the fourth, then something may be amiss. So just a dimension check on your work there. Now, in steel design, they don't necessarily like to use moment of inertia. They like to use this thing called the radius of gyration. I hear there's no laughter involved. Okay, consider the fact that we can take a rectangular section and calculate an Ix for that section. What radius of gyration basically says is that we're going to take that same section there, and I want to keep the area the same, but I want to create the same Ix by just simply moving all of that material off into one little thin infinitesimal strip here. Goes on and on and on. So I can take that same area, and what I'm going to do is take that same area, and I'm going to move it off a certain distance that I'll call kx. And I want that same moment of inertia. So basically, all we're doing is really just describing this moment of inertia in terms of just a single variable now, that k. This is 2. Okay, so if I want to consider doing that same approach where I want to integrate that, that's actually going to be a really nice, easy integration. I'll set up my integration like I've done before there. But since this is infinitely thin, I don't even need to do the integration because it's infinite, basically. What I find then is then that this kx then is going to be the thing that's going to describe and again, like I say, the steel industry kind of likes this. My square is not where it should be. So just simply expressing that, this k of x, this radius of gyration, is just simply that moment of inertia divided by the a. Or the square root of that quantity. And the same sort of thing there. So basically, it's just another way of describing this. The steel industry tends to like it a lot better in terms of describing their materials and their pieces and stuff. But it's just another way of expressing that moment of inertia. And it just pay a little attention to, in terms of how it's related to the moment of inertia. Okay, so what we're going to be doing is going through the first part of this calculation of moment of inertia is going to be the integration approach. On Thursday, we'll talk about how to use the parallel axis theorem, which is kind of a composite approach, but it's a little more difficult than what we did with simple composites there. But we'll start off with a rectangle like so. And we'll do horizontal strips. So we'll set up our integration like so. We'll have our horizontal strips like so. We're going to range between h and b. So again, we'll just simply set up our integration like so. And the first thing you'll notice is that we've got a fixed width there, so we don't have to worry about how it changes as we go up y there, because it'll always be b. My integration will range from 0 to h as I go up from x equal to 0 all the way to h. And my dA basically is just simply going to be b dy. That's the area of this little strip there as I go along there. And again, nice thing it's rectangular, so b won't be changing. Pull the constant out. And then I get to do my fun little integration there. And when I get done, what we'll find then is, and you'll see that in the back of your book, so we just calculated something you can describe very easily. Now, in terms of calculating it this way, it was pretty easy because my horizontal strips, all of that area of that horizontal strip was y away. So it didn't change with y. It only changed as long as y went along there. Let's consider vertical strips. So same problem, except I'm having so much fun with integration that I'm going to try something different here. Okay, and note that my dA now is equal to h dx. So that's my infinitesimal little area there. Now the problem we have here is that if I'm trying to do Ix, it was easy in this case here because when I did my infinitesimal area, all of that infinitesimal area was y away. And since my moment of inertia is basically describing how that area is behaving away from me, the problem is with my vertical strips here is that the area varies in y. Now if I was going Iy, yeah, that's a nice one because then all of that area is there. But the problem is that if I'm integrating this way, my y varies along that strip there. So I can't just simply go in and plug that in. What I need to do is think about what this strip looks like. What does that strip look like? Is it a circle? It's a rectangle. I just did that over here, right? It's a big fat one, but that's a thin one. So I can take advantage of the fact that I already know that distribution from this calculation here, even for that strip, and instead of using b now, I'll just simply use my dx. So it's that same form there, but now instead of a constant b, I'm going to be using a constant dx. It's infinitesimally small.
How do the vertical strips vary in y? Question.
Well, remember, what we're talking about when we do this moment of inertia is we're talking about a measure of things that are going on at a distance away. When we were looking at fluid, how much force is acting out there. What we're talking about is how much area is away from this x. And this is basically what this moment of inertia is describing, and that's why we have things like eye sections and stuff. A lot of that material is way out here. So it varies in y when we think about that, because the y squared, anywhere I look on here, y is going to be different, right? So what I'm going to do is take advantage of the fact that I've already calculated that here, but it's just really tricked for integration to get it to integrate properly. But it's recognizing the fact that that strip, if I was going to do it about iy, that's the way I want to do it. Perfect. But in terms of ix, since it varies in that y, I need to have to capture that variance that's going on there. So, and that's what we'll finish up here. And just basically what I wanted to prove to you. It is just another way of integrating it, but you have to be a little careful in terms of which one are you doing. Okay, now what we'll do is, and the way most things are going to be given is in terms of the centroidal axis. So we'll go into our problem here. So we'll use the same one here. But what I'm going to do a little bit differently here and your author likes to use prime to indicate that we're using a centroidal axis there. So we know the centroid of a rectangle is going to be in the center there. So same approach, except that what we're going to do now is look and calculate this about the centroid. Now this integration is going to be a little bit different because now I'm in the middle there. So my range of integration will now change from 0 to h, from minus h over 2 to h over 2. Same section. And then noting my dA is simply going to be b times that dy section there. Okay, when we start plugging those things in, however, we end up with a different number. Yeah. Thank you. So what we find now is that I can't even spell today. That we can't just get one number. We're going to be finding that depending on what axis system we're at, basically, it's going to be dependent upon our number for our calculation of moment of inertia is going to be different.
But it's always going to be smallest around the centroid.
You're one step ahead of me there. Perfect. Yep. Mm-hmm. That's my little golden rule that I was going to put up at the end, and you beat me to it. Okay, you get extra points. Spoiler alert, yes. But that's a good point. Well, and I will write it out. But basically, as you know, what we're going to see then is that the smallest moment of inertia is going to be at the centroid there. And when you think about it in terms of when you're going to be dealing with stress, so that means it's going to be bigger if we have pieces that are farther away. And that's the concept behind things like eye sections and stuff. What we're going to find is that most of the stress is going to be out there at those far points. So we want to get as much material out there to do the work. And that material in the center here basically isn't going to be doing much. And that's also based upon that distribution when we thought about the distribution of stresses. They look like this in a bending situation, and you'll see that there isn't really much going on there. So that's the concept behind an eye section there. There is shear and stuff we have to worry about, so that's a whole other force that we have to worry about. But in terms of the bending stresses and stuff, most of the action's going on out here. So that's why we use this moment of inertia, because it helps us describe how much material can I get out there. And when you look at an eye section, one of your homework problems that you'll do, it'll be looking at a square section versus an eye section using the same area. And what you'll find is that it'll be a much bigger number, but we kind of like that because if all the stresses are out there, then we can carry a lot more. We can put a lot more material out there. So, but the first part and what we'll be doing in terms of this section is just simply going through our calculations. We're going to be doing integration. And if you thought you got out of integration, it's going to keep coming back to haunt you. So again, basically, it's a simple area that's described, and if you get to work in aerospace and that sort of thing, you might be dealing with turbine blades and that sort of thing, where you are going to be dealing with things that are cut by machines that might be cubics, cortex, and that sort of thing. We got enough handouts? Okay, so we're going to determine by direct integration the shaded area with respect to the y-axis and then also with respect to the x-axis. Pretty straightforward. We'll look at it a couple different ways. So what's the first thing we should do? That helps. Yeah. What do we know about y? What do we know about that curve? Ah. And you're going to see this in EIT exams and that sort of thing. They're always going to be throwing things at you like where they'll throw a constant at you and you need to solve for the constant. So good practice. But solving for k, again, what we've got is two endpoints there. So what we can do is simply plug through all of that, plug in the endpoints there. We'll find that k is equal to b over a to the 1/3, or yet another way to express it. This is now what our equation looks like. So you'll often see situations like that where you're going to have to go in and solve for that little constant. Okay, so we'll consider IY. And we'll do it with the vertical strips. I guess I'll just set that up over here. Okay, so we set up our vertical strips, and again, it's rectangular. It's curved a little bit at the top, but again, since we're taking an infinitesimal area there, we can consider that a rectangle. And that area is going to be y dx. So whatever that y is on the top there, it goes all the way down to y equal to 0, and then its width is dx. Now what we'll do is substitute in because we want to get it in terms of x. We want to get everything in terms of x. We got a dx that we're going to be using. We need to get things in terms of that. And we'll set up our form for our moment of inertia by simply, in this particular case, x squared over dA. Oops. Now, x squared and then x to the 1/3. dx. So I'm just simply substituting in my dA. And in terms of integration, what I want to do is pull out all of the constants. And then multiply all of my x terms together, get them all put together. In this particular case, it's only 1. And then I do my integration. Like I do before, even though it's a fraction in there, we can still deal with it. So I do my integration, I raise it by 1, and then divide by that exponent, and then range it between my 0 and a there. And we get it in terms of b and a there. And again, when we talked about dimension check there, my units are going to be length to the 4th. Each b and a are all length there. So I've got it in the right terms there, or right units. So a little messy, but pretty straightforward. Now, that's 9.2, I think. 9.6 then wants us to look at Ix. And we'll probably want to consider doing that one horizontally. Oops. And the other thing, too, is I want to express my formula now, since I'm interested, this is infinitesimally thin this way, but my area now is going to be composed of this edge versus this edge. So I need to describe this edge in terms of x now. So I just simply take the expression that I solved for in the first problem there, y, cubed everything, and I end up with now an expression in terms of x. And the reason why I want to do that is again, what I want is this dA. And I've got a border here of A. And then as I vary, though, unfortunately, in terms of that horizontal case there, this endpoint changes from 0 all the way up to A there. So that border changes as a function of that y. So that length there in between here is just simply going to be A minus whatever x is, depending on how high I am. So I need to substitute that in. And the key thing is now then I've got my expression in terms of y, so I can do my integration now in terms of y. So I go ahead and set up my integration as before, or maybe we'll put that on the other board here. So I just simply set up my expression. Again, don't forget your y squared term there. We need to put that in there. OK, then I'm going to multiply through by y. So now I've got it set up to do my integration. Go ahead, do my integration, increase those exponents by 1, divide by that. And then just simply plug and chug, do the algebra. And then we end up now having an expression for that I of x as ab cubed. And again, dimension check there. It's in terms of length to the fourth. Now, what we saw when we did it this approach is that we found that, okay, sometimes it's maybe a little bit harder because when we realize that we end up with having two edges there and one's varying and that sort of thing, it becomes a little more complicated. We can consider doing this again with the So we'll do the same thing, but this time what we're going to do is use the vertical strips again. But we're going to use our little trick. And noting that I'm doing I of x, but I'm going to use these vertical strips. So I need to take that advantage. Recall for the rectangular area, we had that. So we can set this up in terms of that infinitesimal now rectangle. See, where did that come from? Oh, need to introduce something here. What did I do? Yeah, hold it. What did I do? Where did that go? Where did that term come from? I'll have to scratch my head about that one. I don't know why that. Let's think here. We've got that. We've got h cubed. Our b is that.
Are you trying to make it? Are you trying to get to the bh cubed over 3?
Yeah, I've got my bh cubed over 3 here. I'm just trying to figure out how I got it into this equation. So I got my ix equal to dix. What am I forgetting? So I've got my y. So I get b cubed over 3a. Let's see, does that make sense? I'm thinking I've lost something here. A squared term again. I keep losing my x's. So if I were to follow that through, okay, so what did I miss here? Well, I'll figure it out and bring it up to you on Thursday. But again, what I'm trying to indicate here is sometimes when we do the horizontal strips, what we find then is that having those two different borders, it's a little more difficult. Sometimes using the vertical strips, even in a case where we're trying to find I of x, that we can take advantage of this little trick here and make a much easier calculation. That one, lots of algebra. This one we were able to do in a couple of steps. So just to summarize, though, let's summarize what we've talked about. Okay, so it's measuring the object's changes to rotation. And again, when we think about that bending, what we're talking about is that plane section there that's going to be rotating internally in the beam there. So it's talking about how much resistance I have to that change. So the bigger I have, basically, the more resistance I have, the more moment I can carry. So it basically, again, is a description of our capacity to resist, not loading, bending. Again, that rotational force. And the other thing we learned is depending on what axis system we're talking about there, it will be different value. We saw that when we looked at the base and when we looked at it at the centroid. Units will be length to the fourth. And I promised you that little, where did my little note go? Actually, it's in the parallel axis theorem is where that little note is, but we'll go ahead and put it there again, O2. And what we'll find is then it'll always be the smallest at that centroidal axis system. And that'll make a little more sense when we actually do parallel axis theorem. Okay, that's it for today.